Okay, guys, so let's start. Good afternoon, everybody. Let's start. So in this course, I explain number one. If I give you a function, something like, for example, f equal xy or x prime or x prime y prime, something like that. If I give you a function like this one, you know easily how can you make two statements, right? You know how to do it. Okay. As I said, you have to put all possible cases here. You have x and only x and y. You have to put all possible cases here, and then for every case here, you need to plug in the values of x and y, and you need to calculate f. Just you know that, right? Last lecture, I started to explain what if it is the opposite. So what if I give you the two table and I want you to create the function? Okay, and I explained it in two different ways. You can calculate this function if in the format of SOP, sum of product. Also, you can calculate if in product of sum. Okay, as I explained last time. So given a two table, how can you calculate a function? Okay. One more thing, guys. I made it very clear that the function you have here, the function you calculate here, this function is not simplified. It's like, I can say it's like a raw function. It's not simplified. You need to simplify it, okay? You can simplify it using algebra manipulation, as we explained before, or as I'm gonna explain in chapter 3, you can use maps, okay? And maps, as I told you, usually we use maps honestly, okay? Because it's much easier than algebra manipulation. Someone can ask me, so which one we are going to use the most? Function to truth table or truth table to function? To be honest with you, I think most of the time what's really important is truth table to function. I'm going to tell you simply why. When you design a function, if I want to design a function to do something, I want to design a logic circuit. When I design the logic circuit, number one, I have to create the truth tables that give me the functionality I want to do, okay? And then I have to convert the truth table into function. That's usually we do it. I give you one example. You remember in I think in lab 2, one of the labs, there was a tutorial on how can you use digital tools. And in this tutorial, I explained what we call a majority function. Majority function. Okay. So in majority function, I want to design a logic circuit. This logic circuit has 3 inputs. You can call them X, Y, Z, and it has one output F. Okay. I want this circuit to give me 0 when the majority here in the input is 0. F give me 1 when the majority here are 1s. I wanna design a function to do something like that. Okay. So number one, you have to start with the truth table. I'm just giving you one example. If I want to design a logic circuit to do something, what should I do? Okay, but we're going to do that all the time. It's the same way. Number one, you have to create the truth table, and then from the truth table, you have to create the function. Okay, so the way we have to do it here, guys, is you have X, Y, Z, and then you have F. So number one, I have to create the truth table of the function I want to create. As I explained before, you have to put all possible cases here for zeros, for ones. Okay, 2 zeros, 2 ones, 2 zeros, 2 ones, 0, 1, 0, 1, 0, 1, 0, 1. Okay, and now giving this input, what do you want to what you want the output to be? Okay, Here the majority is 0, so I want the output to be 0. I'm designing, that's a design. I select, give it this input. What is the output? I want it to be 0, okay? Now, because this is the majority, zeros are the majority. Here also the same thing, zeros are the majority. Here also I want to see 0 because it's a majority. Here in this case, I want 1 because this is a minority. Majority. 1 is the majority here. 0, right? Here 1, 1, 1. Okay? So I want a function with this input to give me this output. Okay. Number 2, once I do the design this way, number 2, I have to convert this function into, I have to convert this f here, I have to write it in the format of a function. Okay. And that's what I explained last time. But again, is that everything? No. After you get this function, you have to simplify it, either using algebra manipulation or using maths, and most of the time I think we'll use maths because it's easier, as I told you. So let me remind what I told you last time. What if I want to design f here in sum of product? Sum of product. You remember what I said last time? Number 1, you have to look for zeros. Okay. How many zeros I have? I have 4 zeros. That means I have 4 terms. I have 4 terms, and these 4 terms are ordered together. Okay. So the first term here should be, every term has to give me, I have to use AND because this is product, sum of product. So this term here, every term has to use AND, and this AND has to give me 1 in this specific case. So to give me 1, so I'm gonna take Y, I'm gonna take Z, but for X, I'm gonna make it X prime. So here here should be X prime YZ. Okay, so that when the input 0, 1, 1, okay, all inputs are 1s, output is 1. Okay, so for this one here, it's the same thing. Whatever 1, I'm gonna take the same variable. Whatever 0, I'm gonna take the prime of this one. So here it's actually X, Y prime Z. Okay, what about this one here? It's X, Y, Z prime. What about this one here? X, Y, Z. Is that okay? And I'm gonna say f is actually equal to x prime y z, or, which is the first term, or x y prime z is the second term, or x y z prime, or x y z. Is that okay? That's what I explained last time. Okay. So by the way, these terms, every term here we call them min terms. Okay, so here, this is row 0, row 1, row 2, row 3, row 4, 5, 6, and 7. Okay, or even this is number 0, number 1, when the input is 0, 1, 2, 3 until 7. Okay, so this one here I'm gonna call it M3, min term number 3. This one here I'm gonna call it M5. This one here, M6, M7. So I can write this function in a different way. I can say f equal min term number 3, or min term number 5, or min term number 6, or min term number 7. Okay, because these are the location of ones. I can write in a different ways. So again, this we call them min terms. Okay, we don't have this one here because zeros. I'm not going to take the min terms here. I'm going to only take the min terms of ones. So let me just ask you a question. So given, if you know the input 0, 1, 1, can you calculate the min term? Yes. How can you do that? Any 0, I'm going to take the prime of this variable. Any 1, I'm going to take the same variable. So here in this case, x prime yz. Is that okay? Can I do the opposite? Can I do the opposite? So if I give you this one, if I give you the min term here, x prime yz, can you know what is the input in this case, or you can know what min term is this one? Yes, you can know. Simply, you can do the opposite of what I did right now. Any variable, so it is 1. Any prime should be 0. So in this case, so if I give you this one here, okay, as a 1 term, can I know what is the min term here? What is the input, or this one is corresponding to which min term? The answer is yes. I'm gonna do the opposite of what I did right now. Any prime, so this one actually 0, 1, 1, which is number 3. So this one min term 3. Okay, I can do the same thing here. This one, there is 2 prime, so 1, 1, 1, which is min term number 7. Look at this one, easy. 1, 1, 0. Any prime is 0. Okay, so this one should be 0, 1, 1, which is number 6. Okay. So again, what I have taught right now, and you should learn, number 1, given a function, how can you calculate the midterms? Okay, and I'm gonna calculate the midterms only for once, and then I'm gonna OR them together to get the function, and I can represent the function in this format this way, or I can represent the function this way. I'm going to say min term 3 or min term 5, min term 6 or min term 7. It's the same thing because I'm calling this one min term 0, 3, 5, and so on. Also, you should know for every row, how can you calculate the midterm? Just in case, you can do the opposite if you want. So if I give you a term, midterm, how can you know which midterm is this one? Okay. Any questions? One more thing I can do here, guys, and we will do it all the time. You need to understand it. I can also represent the function in a different way. I can say f equal summation of midterms 3, 5, 6, 7. So this is also another way to represent the function. So what this means, if I tell you this is a function, what it means? It means the location of the ones are at row 3, 5, 6, 7. So I give you the location of the ones. So if I give you this one, can you make the truth table? For sure I can, because I give you the location of ones, because these are midterms. So here I'm telling you, if you see a function like this one, I am telling you here, the midterm is 3, 5, 6, 7, which means the ones are in this location, 3, 5, 6, 7. Okay, what about the other location? So still we have location 0, you have location 1, you have location 2, you have location 4, is that right? So we still have 4 more locations. Okay, these are the location of ones. That means the other locations are zeros, because we don't have other option. You understand what I'm saying? So if I give you the location of ones, that means the other locations are zeros. Okay? So let me tell you the conclusion now. To represent a function, to give you a function, I can give you a function, number 1, in a truth table. So I can give you this truth table, and you have a function here, 0, 0, 1, 0, 0. This is one way to express a function or represent a function. This is one way. Another way to give you a function this way. Another way, I can give you a function this way. M3 or M5 or M6 or M7, which are the main terms, which are the location of ones. Okay, I can also give you the function this way. So if I give you the function this way, so that means this function, these are the location of ones, because these are main terms. Main terms means the location of ones, as you see here. Any question? Okay, any questions? I'm going to repeat this slide again. I'm going to repeat everything I did here. I'm going to repeat it again, but for POS, product of sum. Okay, think about it. Think about it. How it would be different. Okay, number 1, as I said last time, we're going to work on zeros, not ones. This is the first difference. Okay, if you want to create product of sum, we're going to work on zeros, not ones. And instead of using min terms, I'm going to call it max terms. So here we have max terms. So max terms means this is a location of ones, zeros. Again, what I'm saying, I'm going to repeat the same slide again, but for a product of sum. Number 1, the difference is, as you will see, okay? So I'm going to do it in details, but I just want to give you idea about what are the differences. Number 1, we are going to work on zeros instead of ones. The location of the zeros here, I'm going to call it max terms. So the word max terms are used for the terms of zeros, okay? Remember last time I told you instead of using the format of this one has to be something like X or Y or Z. Also, I'm going to change the format, so I'm not going to use this format because this format is actually for sum of product. Now I'm gonna do product of sum. Okay. One more thing, as you will see. Okay. For example, here, if I want to represent this function in max terms, as you will see, I'm going to say f equal instead of summation, because summation means all, or. Okay. Here I'm going to use by, and then I'm going to say, or I can. Okay. I'm going to write this one in a different way. The function here. So I'm going to say we have M0. I'm going to use uppercase M just to differentiate between min terms and max terms. In min terms, I'm using lowercase m. But in case of max terms, I'm going to say M0 and M1 and M2 and M3. I can write it. It's the same function here. I can just rewrite it this way. Also, this function here, I can rewrite it this way. F equal by for summation, sorry, for multiplication, by m of 0, 1, 2, and 4. So what this means? It means these are the location of the max terms. That means these are the location of zeros. Is that okay? So I can represent the function this way. For sure, if I give you the function in min terms, can you get this one? Or I give you this one, can you get this one? The answer is yes. Because these are the location of ones. If I know the location of ones, I can easily know the location of zeros. If I give you the location of zeros, you can get this one here. These are the location of ones. Anyway, I will give you the details. You know, I just want to link. I just want to tell you what I want to tell you is I explained everything here in detail for some product. I just want to tell you product of some, almost everything is the same, but I'm going to do some changes as you will see right now. Okay, so let me finish it first, and then I'm going to take questions. So now I'm going to repeat everything again. You have here X, Y, Z. You have here 4 zeros, 4 ones, 0, 0, 1, 1, 0, 0, 1, 1, 0, 1, 0, 1, 0, 1, 0, 1. And then we have F here, okay? So here's the majority 0, the majority is 0, the majority is 0, the majority is 1, the majority is 0, the majority is 1, the majority is 1, the majority is 1, okay? So this is the function I have, okay? I wanna represent this function in product of sum, So as I explained last time, the way you have to do it, number one, I have to work on zeros, not ones. This is number one. So now I have 4 zeros, that means I should have 4 terms multiplied together. Again, the word multiplied here means and, okay? So let's take the first step. You remember how, so here actually this one should be or, I need 4 ors, right? Every term has 1 or, everything should be ended together. This is product of sum, okay? This is product of sum. We have sum, product is them together, okay? This is what it means. Anyway, and as I told you last time, the way I have to do it, so here, in order to get this term, so now I need 4 terms, and then I'm gonna, these 4 terms, I'm gonna end them together. So how can you get the 4 terms here? As I told you, I need to find here, I need to find, I need to make or, so that the output is 0. I need to make or, so that, what should I put here in the input? So that I get 0. Okay? So in this case, the way you have to do it, if it is 0, just keep it, because you know in case of or, I'm going to get 0 when all inputs are 0. So if the variable is already 0, I'm going to keep it. If it is 1, I'm going to flip it. Okay? It's a little bit confusing because what I'm doing here is the opposite of what I did before, but you need to learn it. It's not hard. Okay? I changed it because this is or, the other one was and. And in the other case, I have and then I want to make the output 1. So I have to make sure our inputs here are 1s. Now, because here I'm using or, I have to make sure, and I'm working on zeros. So I have to make sure here is the output of 0. So whatever input is 0, I will keep it. Whatever input is 1, I'm going to flip it. Very simple, very easy. So in this case, this one should be actually X or Y or Z. So if I use this gate, so now I am sure in case of this input, this gate is going to give me 0. And that's what I'm looking for. I'm looking for a term that gives me 0 in this case. Okay. Let's look at this one here. This one, x is 0. So I'm going to make it x, or y is 0. Okay. Now I'm going to say z prime. So that when this one is 1, should be 0. So that all inputs are 0 to get 0. Okay. For this one here, x, or y prime or z. For this one here, x prime or y or z. Is that okay? And last time I explained the logic behind it. The logic behind it, when this is the input, this gate gives me 0. And any other input is going to give me 1. Right? Same thing here. And because all these OR are connected to AND, to get 0 here, it is enough to have one input with 0. It's enough to have one input. So that's why when this is the input, I am sure I will get a 0 because I designed this gate to give me 0 for this input. Okay? All other gates are going to give me 1. So it's actually 0, 1, 1, 1. So I'm going to get 0. Okay? Same thing here in this case. The second OR here is going to give me 0. That's why the output will be 0. In these cases here, in the cases of 1 here, as you see, all of them, because I design every OR to give me only 0 in this case, and any other case will give me 1. You can try it by yourself. Okay? Anyway, so now I'm going to say the function if it's in product of sum, function if is actually x or y or z, and x or y or z prime, and x or y prime or z, and x prime or y or z. Is that okay? Remember, also last time I told you, for any product of sum, I can design it only using NOR gates. And any sum of product, I can design only using NAND gate. That's what also I explained last time. Okay? So I can use only one type of gates, NAND or NOR, to design the whole circuit. Okay? Anyway, so this is one way to express the function. These terms here, I'm gonna call them max terms. Max terms. So, okay, so this is max, and then I'm gonna use uppercase letters. So this is here we have M0, so max term for row 0. This one here we have max 1. We have here max 2, okay, and we have here max 4 for number 4. And now so this is max 0, max 1, max 2, max 4, okay? Max terms, okay? So now I can define this function in a different way. I can say f equal to m0 and m1 and m2 and m4. Okay? I can also, and most of the time we will do this way, I'm going to say f equal by, okay, m by m of 0, 1, 2, and 4. Okay? So here I'm telling you, I can define the function this way. When you see by and you see uppercase m, that means these are max terms. These are the location of zeros. That's why I define the function this way. Okay? You have zeros in this location. What about the other locations? They have ones. It's enough because I have only 2 choices, right? So if I give you 1, that means the other locations should have the other one. Okay. What you should learn now, guys. So if I give you this one here, can you, for example, if I give you x, y, z, can you know which main term is this one without making the whole truth table? Answer for sure yes, because the way you can know any variable without prime, so it's gonna be 0. So this one 0, 0, 0. Okay, so if I give you this one, you can know this actually max term 0. If you see this one, so 0, 0, 1. So this should be max term 1, and so. Any questions? So now I can define a function in different ways. One way, as I told you, I can give you the truth table to define a function. So if you have f this way, this should be enough to represent or to define a function. I can define a function this way, I can define the function this way, or I can define the function this way. Is that okay? One more thing, if I give you max terms, can you write the function in min terms? Yes, that's easy. So f should equal summation of small m of what location here? So these are the location of ones. These are the location of zeros. So anything missing here has to be here. You got what I'm saying? So if I give you max terms, you can easily get the min terms. If I give you the min terms, you can easily get the max terms. Because max terms are the location of zeros, min terms are the locations of one. So here, in this case, we have 0 and 1, 2. So we don't have 3. There is no 3 here. That means that 3 is 1. It's not in the list of zeros. So it should be in 1. We have 4. So now we have missing 5, 6, 7. So if I give you a function in max term, you can make it in min term, and if you min term, you can make it in max term. Any questions? Before I take this question, I want to just highlight something again. I will explain last time, but I'm going to say it again. Guys, this function that I make it in product of sum is exactly equivalent to this function that I made in sum product. Equivalent. Both function I can do the same thing. Both function are going to give you this truth table, but I'm doing it in a different ways. One that can be implemented only using names, the other one can implement it using nodes. But as a logic function, both of them are equivalent. You know what equivalent means? They are doing the same thing. Yes.
From this notation, how would you know how many inputs there are?
Yeah, that's a very good question. Okay, it's my fault. Okay, so I can, if I say f equal whatever, I can't know how many inputs, right? I'm not doing magic. I can. Okay, so actually, you have the way we have to do it. I have to say f function of x and y, or x, y, and z. So I have to tell you, I have to write in this way. I'm just lazy, so I just say f. But yes, that's a good point. Okay, this is the same question with semester. So here, yes, if I have to tell you a function of x, y, z, it's not measured. Okay, so you have to tell me. This is something you have to tell me how many variables you have. You got what I'm saying? So yes, I have to write it this way. It's not something you can guess. Any questions? Okay, let me go through the slides here to see if I missed something. So here I'm explaining some of product. How can you calculate them here? You have to work on ones, and this is called min terms, as I told you. Here I explained the max terms. Okay, so you have to calculate them this way. This max terms, you have to work on zeros. Okay. Anyway, you don't need to do, just, I don't want to confuse you. You don't need to do what I did here. Okay. What I did here, I want to prove to you why I'm going to make it this way. So here I implemented f prime. I used the min terms, and then because this is for f prime, okay, for min. So now I'm going to use De Morgan. Once I use De Morgan, I can get this one. But again, in exams and anything, you don't need. It's like a proof. I want to prove you to have to work it, so you don't need to do this one. You can just work in zeros, as I just explained. Okay, you don't need to work on f prime and then change f prime to f as I take you. You don't need to do that. Just work in f as I explained. Work in zeros. Okay. Here again, I want to prove to you I got the same function. I represented it in sum product, and I represented again using product of sum, as you see here. I just want to show you here using algebra manipulation that these two functions are equivalent. So here I started with this one here. I started with this function, and I'm going to give it to you. I did some algebra manipulation. I got this one. I got the other function here in the product of sum. I simplified it. I got the same function. So here I want to prove to you that actually, yeah, the two formats are equivalent. Actually, I don't need to prove to you. You know why? I'm going to tell you why. Because both of them have the truth table is telling me that. So you know, one way to prove equivalence is by using the truth table. And yeah, this function has this truth table, and this function has this truth table with the same equivalent. So if you look at this column, they are exactly the same thing. But anyway, Also, you can learn something else from this slide. What you can learn from this slide is, as I told you, the function I want to calculate this way. This is, I can call it a row. It's like a row function. It's not simplified. Okay, that is why you need, once again, the approach I explain right now is, you have a truth table. How can you get a function? Okay, I got a function. Now you need to simplify it. Okay. So what I did here, I simplified it using algebra manipulation, and I got this function. So this function, these two functions are equivalent. Okay, but this one is not simplified. This one is simplified. Same thing. This function and this function, these two expressions are equivalent. Okay, so actually these three expressions are the same thing. It's the same thing, but this is the simplified version of it. Okay. Here I used algebra manipulation to do simplification. In next chapter, I will show you how can use maps to do simplification. Okay, don't be confused. So what I explain right now, SOP or POS, I explain, given a truth table, how can you get a function? But this function is not simplified. You need to simplify. Okay. Here I'm explaining min terms and max terms. We use lowercase for min terms, as you see here. We use uppercase for max terms, as you see here. So if you have here row 0, row 1, 2, 3, 4, until 7. So now I'm going to have here min terms for this one. This one can have min terms this way, okay, or it has max terms this way. Okay, this one has min terms this way or max terms this way. So here I'm showing you how to calculate for all of them. But when you have a function, you have to calculate the min terms only for the location once. But here I'm showing you all of them. Okay, here I'm going to calculate this one only for the location of zeros. You got what I'm saying? But I'm showing you how for every row, how can you calculate the min terms and max terms. But actually, for any function, I'm gonna only take the ones the min terms that have ones or the max terms that have zeros. But I'm showing you for all of them how can you calculate them. Okay. Any question? So these are min terms. This is max terms. We use a lowercase, uppercase. This min term for row 0. This is max term for row 0. You need to know how can you calculate them. Tuesday, there will be a quiz in Tuesday. Okay, it's very easy quiz. I will give you a truth table, and then I'm gonna ask you write the function, write f in sum product and also product of sum. That's it. I'm not gonna ask you to simplify. Just write the function. Similar to what I have just explained here. Everywhere, okay? As I explained, I'm gonna give you a function like this one, a truth table like this one, and then I'm gonna ask you to give me this function and give me just a function like this one. Okay? Any questions? That's very easy. Okay. Here I'm just telling you I'm gonna represent the logical function in a different way. That's what I have just explained. So if you have a function this way, sum of product is this way, okay? So I can represent it this way as well, because this is min term 3, min term 4, and so on. And if you have this function, as I told you, you can easily know what are the min terms. For example, here, so this one has to be 1, 1, 1, which is number 7. So this one 1, 1, 0. You got it, since that's what I explained. So this one should be actually number 6. So if you have this one, you can easily know what's the number of this one. Okay. So I can make it this way, or I can make it this. And I have to define the function this way. I have to tell you how many variables we have. Is that okay? Same thing for max terms. So if you have a function this way, I can represent, or I can define whatever word you want to use. I can define the function this way, or I can define the function this way. So all of them are connected. Okay. Yeah. So here, yeah, that's just a very easy thing. So here I give you this function. These are the locations of ones. Can you represent this function in min terms? Yes. Okay, so actually this is 0, 1, 2, 3, 4, 5, 6, 7. So actually here, so this one should be location of ones. So min term is 3, 4, 5, 6, 7. So if I give you truth table, you can write it in this format this way. Okay? But this is not what I'm gonna ask in the quiz. I'm not gonna ask about this one. I'm gonna ask you have to give me this one. So don't be confused. Give me this one or give me this one. Okay. So here, I can define it this way, or I can define this way. Okay. For same thing for product of sum, but here this time I'm gonna work on ones, not zeros. So I can define this way. So max term is 0 and max term 1 and max term 2. Or I can define it this way. Okay. Any questions? Yeah. This is just another example. So the exam will be, or the quiz will be very close to something like that. I'm gonna give you a function like this one. I'm gonna ask just write this one to this one. Okay. So I'm gonna leave this one to you. This nothing is new. This is exactly similar. So here location of ones. So midterm 1, 4 and 7. So 1, 4, 7. I can write it this way. Okay, and this is you can. By the way, so here actually one here is actually 1 1, 0, 0, and this is x, y, z. Okay, so z is 1. So how can I make this term out of this number? Okay, so it should be x prime, y prime, z. Any 0, I have to make it prime. Okay, you understand what I'm saying? So for example, if you have a function, this function, for example, I have number 14 or number 14, for example. Okay, 14 is 1, 1, 1, 0. This is 14. Okay, can you get the logic term out of it? Yes. For example, here I have A, B, C, D. So in this case, it has to be A, B, C, D prime. This is the midterm of 14. You got it? Same thing here, but here I'm going to work with zeros, max terms. Okay. So here, what I'm saying here, guys, I can represent or I can define a logic function in different format. I can define it in truth table. I can define it in a format like this one, sum of product or product of sum. I can define it using summation this way or using by this way, max terms and min terms. Okay. Here I'm explaining to you from min terms to truth table. So here, if I give you the function this way, how can you make the truth table? Okay, that's what I'm explaining here. Very straightforward. So all what you have to do here, I'm giving you the allocation of ones. So I have to put 1 here, 1 in number 1, 2, and 6. Everything else, I'm gonna put zeros. Okay. So here, as you see here, I put all different inputs. Okay, so I give you this one is given to you. I'm asking you to make the truth table. So here, number 1, you have to put all inputs, A, B, C, and then location number 1, location number 2, location number 6, you have to put ones. So remember, we don't start counting by 1. So here, this is location 0. You can even convert, if you convert this number from binary to decimal, so this makes 0, makes 1, makes 2. Okay, so 0, 1, 2, 3, 4, 5, 6, 7. Okay, so that means location of here I will tell you 1, 2, 6. So at 1 you have to put 1, at 2 and at 6. Any other places I have to put zeros. Easy, right? Also, if I give you this one in min terms, I can easily make it in max terms. So I can say by m of, so I have to put the missing, whatever missing I have to put here. Okay, which is 0, comma. We have only 1, 2, so 3, 4, 5, 7. Okay, any questions? Easy, right? Logic. Any questions? Okay. Same thing here. From min terms to max terms to truth table. So if I give you the min terms, it's easy. You can get max terms. If I give you max terms, you can easily get the min terms. If I give you any one of them, it's easy to make truth table. Okay. So here I give you here min terms. You can easily make max terms. Okay, and then you can make the truth table. So here using the max terms. So these are the location of zeros, and then these are the location of ones. So here I'm gonna in this location here using max terms. So location 0, which is here, location 3, location 4, 5, 7. These are the location of zeros. Very easy, right? And current this way, all of them are the same. Any questions? Yeah, so here maybe something interesting here. So for example, if I have a function like this one, A, B, C, D, And I can define this function this way using midterms, and I can define this way using max terms. So, and so I can, using midterms, I can define a function with sum of product. Using max terms, I can define a function in product of sum. Okay, and this function is going to do exactly the same thing like this function. So if you have the choice, which one would be easy for you? Sum of product, because you have only one term. You get what I'm saying? But if this one is you're going to have 15 terms. You got what I'm saying? So it's going to be easier for me to do that. Okay. So I can see here, if you have the choice and you have more ones, f has more ones than zeros, so maybe sum of product is easier. Sorry, more ones than zeros. So zeros are we have this number of zeros. So max term is or product of sum may be easy for me. It's easy to work on zeros, not ones. Yeah, here I give you one more. Sometimes I put a lot of examples for you just to learn. So here we have only one variable a and b. So here min term is 1 and 2, max term is 0 or 3. Okay, so here I'm explaining something that what I'm explaining here is if I give you a function this way, okay, which you can say this is a simplified function. Okay, I can ask you, I give you this function, and then I can ask you, give me the midterms or give me the max terms. How can you do that? So what I'm explaining now, if I give you a simplified function like this one, and then I ask you, give me the midterms or give me the max terms. Okay, there are two ways. Number one, you can implement this function using truth table. So here I can have A, B, C, and then you can have F. So you need to calculate this one for F. Okay. So given this function, you can make a truth table, and then once you have the truth table, everything easy after that. I can get the midterms from the location of ones. I can get the max term from the location of zeros. This is one way to do it. Is that okay? I think I explained it here somewhere. Yeah, look here. So I have this function. So using this function, I'm gonna make this truth table. Okay, so we have input 0, 0, 0. I'm gonna plug in here 0, 0, 0. Output is 0. For every input, I will do that. So for every input, I'm gonna apply it here to get F. Okay. Once I have F, okay, that's easy now. So these are the location with the max terms. Max terms are here. So these are max terms, and ones are actually the location of min terms. Is that okay? It's one way to do it. There is another way to do it, which may be a little bit more complicated, but there is another way to do it, is by using algebra manipulation. Okay? I'm going to tell you what is funny here. What's really funny here is, so here I have this function. I'm going to do algebra manipulation. I'm going to tell you how, and then I'm going to get this function here. Once I get this function where every term has all variable. So what's the problem here? This one is AB. Okay. If this one in max term or min term is, every term has to have all variables, ABC, right? So if I go back to some case, if I go back for any max term or min terms I explained before, so every term has all variables here, okay? But what happened is that after I did I started here and then I went here to do simplification. After I simplified it, I got this one. So originally it was something like that, and then I did algebra manipulation to simplify it, I got this one. Okay. For some reason, or maybe I want to be silly, or for some reason, I want to do the opposite of simplification. Usually we don't do this way, but anyway, just to learn, good to learn how to do. It can be like a practice on algebra manipulation, but anyway. So here what I'm going to do here is the opposite of simplification. I'm going to call it expansion. You get what I'm saying? So if you have this one is already in the format of min terms or max terms. How can you know? If you look at every term here, every term has all variables. So this one is already in the format of min terms. Okay. If I do algebra manipulation, I'm going to simplify to get this one. Now I want to do the opposite. I'm going to give you this one, and I want you to give me this one here. Okay. So it's the opposite of simplification. I'm going to call it expansion. So let's see how can I do it. Very simple, just simplification. So look at the idea. Okay, look here this term. In this term you have A and B. What's missing? Missing C, because I told you every term should have the three variables A, B, C. So here I have A and B. Missing is C. So what I'm going to do in order to expand it. So I'm going to say AB is equal to, it's the same thing like AB, C or C prime. Wait a second, what I'm doing here. Very simple, as I explained before, this one is equivalent to 1. It's like I multiplied by 1. I didn't do anything. Here I made end with 1, multiplied by 1. I didn't do anything, okay? But, okay, so here it's going to be C or C prime, okay? And then after that, I can do distribution. So now AB should equal to ABC or ABC prime. I expand it, okay? If I give you this one, I ask you to simplify, you would come to here. You would take AB common and C or C prime equal to 1. So what I'm doing right now is the opposite of simplification. Okay, we call it expansion. Anyway, so now I'm done with this term. So this term, I already introduced all variable here. Okay, so this one now, it became in this format. So remember, what min term is this one? This min term number 7. What min term is this one? 110, which is min term 6. Is that okay? So now I found min term AB, this term is min term 7 or min term 6. Is that okay? Something very interesting and very related to what I'm going to teach in chapter 3. So you can see here, guys, if I have min term 6 and min term 7, I can simplify it using AB. Okay? So that's exactly what we're going to do in maps. So I'm going to do maps, as for sure I'm going to explain details. Okay? Every min term has a square. Every min term has a square. So we will find min term 6 and 7, for example, I'm going to put here 1 and 1, and then because they are neighbor, I can combine them together and get EB from the figure. So anyway, I just want to relate to what I will explain what you see here. So here this one telling me if I have min term 6 and min term 7, I can combine them together. This is algebra manipulation to get EB. That's exactly what I'm going to do in maps. So in maps, every midterm is going to be represented by a square in a map. And then after that, I will tell you any neighboring ones, I can group them together, represented by some way, represented them using only one term. Okay? Anyway, forget what I said. I'm going to explain it in details. Okay? Anyway, so now I'm okay with AB. Okay, now let's look at C. So what terms are missing here? A and B, right? Because it has to be A and B and C. So I will do the same thing exactly here. So first I'm going to introduce A, as you see here, A or A prime. So the C is equivalent to these two here, okay? So what's missing? Then I'm going to do the same thing again. Here, this one, I'm going to end B or B prime, okay? Same thing here, B or B prime, okay? So now C alone is equivalent to 4 terms. 4 terms, okay? 4 terms are equivalent to only C. Again, if you do, and this is just fun, if you take this one and you do algebra manipulation, we'll simplify to C. Okay? Now I'm doing the opposite. Okay. By the way, I think I will leave to you. You can think it's very easy. You can think how can you do it. Okay. I will leave it to you. How can you use all this? So by this way, guys, I found what I did here. I just made some algebra manipulation. I found that AB is equivalent to these 2 terms. Okay. C is actually equivalent to 4 terms. Okay. Now this function is equivalent to all these terms. Okay? I'll give you one more example. Maybe I don't want to spend more time with this one. It's almost the same thing. So here you have Here we have A, B. C is missing. C is missing. Okay, and D is missing because this function in A, B, C, and D. So here I'm gonna put C and D, and then I will do distribution. For this one, B is missing and C is missing. Okay, so anyway, so after I did that, I found two terms. I think they are identical. For some reason, I can't see these two terms. Yeah, I think I found two terms who are identical. So I don't need. So look for this one: A prime, B prime, C prime, D. Yeah, look here. So I found this one is repeated here. So that's why I'm not doing simplification, but when it is repeated, because you should not repeat here. Okay, so repeat means I can say 2 and 2. What I'm saying it's only once. That's why I found these two terms are repeated. That's why I'm not doing simplification, just repeat it. I can say one. Same thing for this one. Anyway, so I'm gonna leave this part. Same thing here, nothing is new. Just did algebra manipulation, very simple. Okay. Same thing I'm gonna do it for max term expansion. Exactly same thing. So in max term, number one, I need here. It has to be all terms all terms or together, and then the middle has to be and. Okay. So here again, you have to look for the missing term. So here we have ABC. So what's missing is C. Okay. So I can say A or B. It's the same thing like A or B or C prime. Why? I added 0. I added 0, or I ordered 0 to be more accurate, because this is 0. When you OR with 0, I didn't do anything. Okay? And then after that, as you see here, after that, I'm going to do algebra manipulation to get, so A or B is actually, this term is equivalent to these two terms. In order to convert this term into max terms. Again, I'm going to say it again, guys. In max terms or min terms, they have all variables should be represented here, all variables, okay? If something is missing, I'm going to do algebra manipulation to have it, or to add it to the term, okay? Without changing anything, I just added to 0. I didn't change, okay, anything. Anyway, so after I finished everything, I was able to convert here this function, a simplified function, to the unsimplified function, okay? So this is one term, one term, one term, one term, one term. Can you know? Look here. Which means that's what you need to learn. Which max term is this one? Yes, this should be 0, 0, 0. Think what I did is the opposite. Opposite of when I can, if you have numbers, how can you get the max term? What I told you, if there is 0, I'm gonna represent it using the variable without prime. Now I'm doing the opposite. If there is no prime, that means this is 0. So this 0, 0, 0, so this one is equivalent to number 0. Okay, look at this one. So this one actually 0, 0, 1. So this is equivalent to number 1. This one here, 0, 1, 0. Number 2. This one here, 1, 1, 0. Okay. Any questions? It's not difficult, but you need to link things together. I think this is just an example. I think nothing is new here. So if you have here a function, these are the min term with the location of 1. So if you have, yeah, this is just a truth table. I'm using a truth table here. So these are the min terms. These are the min terms. So from the function. So if you have a function here, you can make a truth table. From the truth table, it's easy. Once you have the truth table, it's easy to get the max terms and make min terms. Okay. Yeah, I think it's the same thing here. So if you have this function, I can make the truth table, and then from the truth table, I can find the max term min terms. I can represent the function in different ways. Any questions? Again, I think the most important slide is this one. Now you should learn, you should understand. I can represent a function in different ways. If I just give you the truth table, this is a represent. I give you the function in a format, in a certain format. I can give you the function in a different format using sum of product. I can give you the function in product of sum. I can give you the function using midterms, a list of midterms or list of max terms. All of them, every one of them is complete representation to the function. So one of them should be enough. And not only that, if I give you the representation, that's what I explained. If I give you the representation in certain format, you can easily get the other formats. That's what I explained. So even if I give you this one, I explain how can you get the other formats. Okay, so I can represent the function in different formats. Only one representation should be enough. And if I give you one format, you should learn how can you get the other formats. Any questions? Okay, guys, any questions? Is that easy or difficult? It's fun. I feel it's fun. I don't know if you have the same feeling. It's easy, right? So I hope so. Anyway, so let's. The last topic I'm going to explain this chapter before I move to the next chapter. Next chapter is easy, very easy. Okay. Next chapter, as I told you, is just we have a function. I want to simplify this function. Okay, but using maps, and maps are much easier than algebra manipulation, as I told you. Okay? So anyway, so the last topic I'm going to teach you here, something we call don't care. You don't care, right? I don't care. So here, don't care. Or sometimes I'm going to call it incomplete functions or something like that. So we call it don't care. Okay, what do you mean by don't care? I'm going to tell you what I mean. I have a logic circuit here. Okay. And the input of the logic circuit should be a number from 0 to 9. Some PCD. PCD means it's a binary number, decimal number, decimal digit, but represented in binary. Okay, so you know in decimal we have digits from 0 to 9. Okay, so here I have input binary, so the input here is a binary, but the binary input is actually a number from 0 to 9. Is that okay? So let me ask you a question now. How many inputs I can have here? How many inputs? Is 3 is enough? 3 is enough? Answer is no. Because as you know, 3 is going to give you a number from 0 until 2 to the power of 3 minus 1, which is equal to 7. So but I need a number from 0 to 9. So 3 inputs are not enough, because 3 inputs are going to give me a number from 0 to 7. Make sense? Okay. So what should I do? I have to add one input. I need four inputs. Is that okay? But 4 inputs are going to give you from 0 until 2 to the power of 4 minus 1, which is 15. 0 to 15. Do you have any other choice? Because if I input 3, I'm going to get from 0 to 7. The input should be from 0 to 9, right? So the other choice is just 4 bits. I don't have any other choice. It cannot be 3 bits and half bit. We don't do that, right? 3 or 4. So, but in this case, yes, the input can be number greater than what I need. That's okay. But so the input here can have a number from 0 to 15. This is the input. Okay. But in reality, the input always will be between 0 and 9. And any number above 9, it should not happen. It should not come. Because this logic circuit should accept the number from 0 to 9. The input always a number from 0 to 9. You got what I'm saying? Anything above, although the circuit is allowing to have numbers greater than 10, greater than 9, but actually in reality it should not happen. Because if you want to do some functionality here, requires that the input is from 0 to 9. Is that okay? That means any number from 10 to 15, these numbers should not come. Should not be at the input. You got what I'm saying? Although the hardware allows it. So the hardware allows me here to put number from 0 to 15, but for functionality, okay? The user, you should not input these numbers. You should not use them because the input has to be BCD. BCD means it has to be between 0 and 9. Is that okay? So let me ask you a question. Okay, so you are telling us the input here has to be between 0 and 9. But actually, because I have four inputs, I can input from 10 to 15. Yes, you can do that, but you should not do that. Okay? Or it doesn't make sense to do that because I'm asking you to enter a decimal digit. Decimal digit has to be between 0 and 9. If you input something more than 9, okay, I don't care. Okay? So, okay. So now the question is that, listen to me. Okay, so you are telling me the user has to input number from 0 to 9. That's okay. What if I input 10? Do you care what output you are going to have here? Do you care? The input itself doesn't make sense. You should not input 10. So if you input 10, I don't care if the function gives you 0 or 1. I don't care. You understand what I'm saying? Same thing. So any number from 0 to 15, I don't care what you are going to get here. Okay? You understand what I'm saying? Because this is not, it should not happen. Okay? But if you put it, I don't care about what you are going to put here. You understand what I'm saying? I don't care about as a functionality. Okay? So as because here this logic circuit should work on numbers from 0 to 9. So if you give me a number from 0 to 9, I will give you correct output. Anything else, I will give you something that, because it's hardware. You input a binary number, you will get a number. That's okay. But there is no logic. It can be random number, it can be any number. You understand what I'm saying? Okay. So now, as a functionality, I don't care if you give here 0 or 1. For me, it's the same thing. I don't care. Right? Okay, that's why you have the term we don't care. Okay, so what's the point here? What do you want to explain? What I want to explain is, so we agree for the number from 10 to 15, if can be 0 or 1, 0 or 1, 0 or 1, 0 or 1. Okay? Because I don't care if it gives you 0 or 1. Okay? Okay. However, yes, I don't care about the functionality. Give me 0 or 1. However, sometimes if I want to simplify the function more, it's better for me to use zeros or ones and zeros. You understand what I'm saying? So now I will try to leverage this situation for my benefit. You understand what I'm saying? So now the question is that here in this case of 10, 11, 12, 13, 15. Okay, what numbers I have to use here, zeros or ones? Okay, as a functionality, I don't care. Okay, but which numbers I have to use to make it more simplified? Help me to simplify it more. You understand what I'm saying? So in this case, I have to look for what is good for me for simplification. Okay, if it is good for me to put all of them once, okay, go ahead. I don't care. If you can simplify the function more, if you make it all of them zeros, yes, go ahead. You understand what I'm saying? That's why we say don't take care condition. Okay, so here I give you an example to understand exactly what I'm explaining here. So here we call it incompletely specified function or don't care. Okay, don't care condition. I'm assuming, look here, guys, usually if you have don't care, so for some reason I have here in this function, this input should not happen. So if it happens, the output is X. So here, what this means, output is X. Same thing here, it's X. What it means, look here, guys. That means for functionality or for this logic circuit to function correctly, for this logic circuit to function correctly, when the input is 0, the output must be 1. When this is the input, the output should be 0. When this is the input, the output should be 1. When this is the input, the output should be 0. However, when this input comes, I don't care if you output 0 or 1. It's not going to impact my functionality because this input should not happen. You understand what I'm saying? That's why you are going to introduce something new here. I'm going to call it X. So for example, I'm assuming here in this specific case, I have two don't care cases. Okay. So this one, that means guys, look here, guys, how many possible cases I have? So I can put 0, 0. Well, it's still okay. It's okay. This function is okay. Or I can make it 1, 1, or I make 0, 1, or I make it 1, 0. All of these are okay because I don't care about the output in these two cases because it should not happen. Okay. But if they come, I have to output something. Okay. Now what I'm saying. Now, okay. So now, which one is better for me for simplification? Is that better for me to put 0, 0? Yes, I can do that. So now I can try all possible cases here. So I can try put 0, 0, and then I put here 0, 0, and then I got some product. I simplified it. I got this one. So here, this is again when you consider 0, 0. Okay. If you consider 1, 0, one of them is 1, the other is 0. I got this one here. Okay, this one here. I got another function here. When one of them is 1, the other one is 0. When I put both of them are 1s, I got this function here. Okay, So that means if you look at what I got here, you can find this one is the most simplified one. So it's for simplification, it's better for me to use 1, 1, 0. You got what I'm saying? To simplify it more. Two things now, two things to finish this part. Two things. Number one, why you are telling me this one is more simplified than the other two? Why you are telling me that? Because the word simplified means, what simplified means? Can anybody tell me? Simplified. Simplified means two things. What are the two things? Can anybody tell me? So I need few terms. That's number one. So the smallest number of terms. So based on the first restriction here, this one has 3 terms. This one has 2. This has 2. So I'm going to exclude this one. 2 terms is better than 3 terms. Is that okay? What else? Is that everything? No. So here also I'm looking for fewer or a less number of inputs in terms. This number of inputs in terms. So if you look this one here, this one has 2 inputs, this one has 2 inputs. It's the same. But this one has 3 inputs, this one has 2 inputs. So this one is better. Okay? This is the meaning of simplify. Remember what I said right now, because that's what I'm going to do in the shot. The meaning of simplify, that means I want to minimize the number of terms. Number 2, I want to minimize the number of variables in terms. That's why I'm saying this one is more simplified than the other ones. Is that okay? This is one thing. There is another thing I want to explain to you. But with the second man, it's very simple. This is very difficult, very tedious. So here, this was easy case because I have 2 variables. So because I have two don't care. In case of 2 don't care, that means I'm going to have how many possible cases I have? 2 to the power of 2. So I have to try the function 4 times. What if I have 3? 3 don't care. So I have to try 8 times. What if you have 4? So I have to try 16 times. You understand what I'm saying? So I have to write the function 16 times, minimize all of them. Okay? It's very tedious, right? Or very, very, very difficult to do this way because I have many combinations with this one. That's why maps are going to be more suitable for these ones. Maps. Because in maps, just by looking to the map, as you will see, usually we don't do it similar to what I explained right now. We need to make function and then simplify. In maps, I'm going to have 1 and then I have x here, x here. So I will see what is good for me to make bigger groups. What's good for me? Is it better for me to take this one 0 or 1? You understand what I'm saying? So I'm gonna repeat this topic again. Exactly the same thing here about don't care in case of maps, because maps are gonna be much easier to decide. Is it better for me to take x as 0 or 1? Better for me regarding simplification. Regarding functionality, I don't care. If the function outputs 0 or 1 for this input, I don't care, right? I'm gonna try to take it for my benefit. I'm gonna try to see which value for x 0 or 1 is better for me to do more simplification. Okay? Any questions? Okay. Let's go to the next chapter. It's very easy chapter. Once you understand it, you will like it more than algebra manipulation. So this function has only one topic. Only one topic. It's about gate level minimization or simplification. Given a function, how can you simplify it? Okay. We already explained how can you simplify a function using algebra manipulation, but maps are much easier for maps. Okay. So let's start with that's what we call key maps or Karnaugh maps, or for short we call it key maps. Okay. So in key maps, I'm going to explain number 1. If you have 2 variables, if the function has 2 variables, how can you make the maps? How can you simplify 3 variables? And then we are going to stop at 4 variables, no more than 4. Okay, so what we're going to teach here. Usually 2 variables. You don't need to make a map. Usually for 2 variables, maybe algebra manipulation is very straightforward, very easy because it's too small. But most of the time, we're gonna use maps for 3 and 4. Okay? What about more than 4? What if you have 5 variables, 6 variables, something greater than that? Usually in this case, we don't do it manually. Usually, in one lab, you can do it either. You can do it side, okay? You need to have a computer program. This computer program, we do that in one lab. You can go either, you can go to an online website, just input the function, and then it's going to calculate the simplified function using maps. But we do more than that, more than 4, it becomes more complicated, and we are going to teach until 4. You know, also the simulator you have, the digital simulator graph, also can do this simplification using, if it is more than 4 values. You will learn, we will do it in one lab, okay? So let's start here with key maps. What do we mean by key maps? So key maps are actually graphical method of visualizing the ones and zeros of a Boolean function. Okay, so as you will see shortly. Key maps are very useful to for Boolean simplification or minimization. Key maps is representation of the truth table using a matrix or using squares or sets. Okay. Okay. So here, first of all, if you have 2 variables, how many? So if you have 2 variables, this is how the map looks like. Okay. What is the relation between number of variables and number of squares here? So very simple. If you have 2 variables, how many cases you are going to have in 2 variables? 2 to the power of 2. That means I'm going to have 4 cases, right? 4 rows. Every row is going to be represented here by 1 square. That is why, in case of 2 variables, I should have 4 squares. Here, in this case, we have 3 variables. So in case of 3 variables, how many cases you have? 2 to the power of 3, which is 8. That's why you are going to have 8 squares here, because every row is represented here by 1 square. Every row in the truth table is represented here by 1 square. Okay. Same thing, if you have 4 variables, so how many squares you have? 2 to the power of 4 or 16. Okay. So now you can know what is the relation between number of variables and number of squares I have here. Very simple, very simple. So if you have a truth table, how many rows you have in the truth table? 2 to the power of n. Okay. And same thing here. So how many? So every row here for the function f is going to be represented here by one square. Okay. So if you have 16 cases, I need 16 squares. If you have 8 cases, I need 8 squares, and so on. Okay. So let's start with 2 variables. In case of 2 variables, how the map looks like. Okay, this is the map for 2 variables. As you see here, I have 2 variables, x and y, for example. So these are all possible cases. So the way I make it, guys, is this is min term 0, min term 1, min term 2, min term 3. Okay. Min term 0, min term 1, min term 2, min term 3. One more thing I'm going to say this is y and this is x. This is x. Okay. So what it means? It means these 2 squares have x, and these 2 squares have x prime. So this is the area of x. This is the area of x prime. Same thing here. This is the area of y, and this is the area of y prime. What do you mean by the area of y? That means, look here, guys, what I want to explain. Very simple, very easy. So again, what I'm saying here, any terms here have x. Any terms here, because this is the area of x, have x prime. Once you can see here, this has x, this one has x. This one x prime, because this is not the area of x. Same thing. This is the area of y. That means this is the area of y prime. I don't need to say that, but if I give you, I tell you, this is the area of y, so the other areas for y prime. Okay? And that's exactly what I did. See what I did here? So you can see here, we have y here, we have here y prime, y prime. You got how I made it? And if you look here, you can see x prime, y prime. You remember this one? Yeah, this midterm is 0, which is equivalent to 0, 0. This one is equivalent to 0 and 1. So this is midterm 1, midterm 2, midterm 3. So here every midterm has one square. And then the last thing I'm going to explain, guys, here is, and then once you have a truth table, something like that, okay, I know this is midterm 0. Here, midterm 0 is 1, so I'm going to put here 1. Here, midterm 1 is 1, so I'm going to write here 1. Here, midterm 2 is 0, 0. So now I'm going to have a map like this one, 1, 1, 0, 0. So this is the first step. The first step is, given a truth table, how can you make a map? Second step, I'm going to work on the map to calculate the simplified function. That's what I'm going to explain next time. Okay? So what I explained today is, given a truth table, how can you represent a truth table in a map? Okay, this you can see this one like another representation for functions. Okay, because if this enough, if I give you this is a function, this is how I define a function. By the way, this is a definition to function. So if I give you a map like this one, I'm telling you min-term 0 is 1, min-term 1 is 1, the other two min-terms are zeros. So if I give you this one, you can make the function. But I want to make it in the format of a map so that, as you will see next lecture, so that I can group. I can make grouping and I can make simplification, as you will see next time. Okay, thanks. Don't forget, there is a quiz on Tuesday. The quiz, I will give you a quiz. I'm going to ask you to write about simplification in some products.